Today, we're going to dig into a really cool piece of material science, one that could seriously change how we build things, from car parts to electronics. We're breaking down a 2023 study from the Journal of Applied Polymer Science. The work was done by a team of researchers, Thiago Augusto, Danilo Carastan, Amanda Santos, and Baltus Bonse. And what they figured out is basically a recipe for supercharging a common, everyday plastic.
So let's jump right in with the big question that this whole study is trying to answer. How do you take a regular plastic, one you might find all over the place, and make it tough enough to handle the heat and stress of something like a car engine? That's the challenge they set out to solve.
And here's our game plan for how we'll walk through it. First, we'll talk about the plastic itself and why it needed this upgrade. Then, we'll look at the experiment they designed. After that, we'll dive into the results, the huge effect of a hot mold, the pros and cons of adding a nanofiller, and whether injection speed even matters. And finally, we'll put it all together to reveal their perfect recipe. Okay, so let's meet the star of our show. We're talking about a plastic called polyamide 6. It's super versatile, but as you're about to see, it has a ton of untapped potential just waiting to be unlocked. So what exactly is polyamide 6, or PA6 for short? Well, it's a type of engineering plastic that's already used in tons of stuff. It's known for being pretty tough, pretty stiff, and it doesn't wear down easily. You'll find it in car parts, industrial gear, even in things like durable fabrics. But here's the catch. PA6 isn't perfect. As other researchers have pointed out, it has its limits. Its overall strength, and especially its heat deflection temperature, that's basically the point where it starts to get soft and lose its shape, well, they aren't quite good enough for the really heavy-duty jobs. The whole point of this research is to smash through those limits. Which brings us to the experiment itself. So, how did they plan to do it? How were they going to supercharge this plastic? Well, they decided to focus on a few key things they could control during the manufacturing process. They basically had three main knobs they could turn. First up, the temperature of the mold. Would a cool mold at room temperature, 25 degrees Celsius, work better than a hot one at 85 degrees? Second knob, injection velocity. Should they fill the mold slowly or really fast? And the third knob, this is the secret sauce. What if they added a tiny amount, just 3%, of nano-sized calcium carbonate particles? And this table right here, this is their whole strategy laid out. You can see it's super methodical. They made 8 different versions to test every possible combination. Hot mold versus cold mold, fast injection versus slow, and with the nanofiller versus without it. This careful setup is what let them figure out exactly what each change was doing. Okay, let's get to the good stuff, the results. And we're going to start with the variable that it turns out made the biggest difference of all, the temperature of the mold. So does a hotter mold actually make for a stronger plastic? And the answer is a huge, resounding yes. I mean, just look at this chart. The blue diamonds show the impact strength, which is just a measure of toughness. See that massive jump between the first 2 points and the next two? That's the hot mold at work, boosting toughness by up to 60%. And the red squares show us why. That's the degree of crystallinity. A hot mold gives the molecules inside the plastic time to line up into a more organized crystalline structure. And that structure is what makes it so much stronger. And you don't even have to trust the chart. You can literally see the difference under a microscope. On the left, you've got the sample from the cold mold. See how smooth that break is? That's a classic sign of a brittle fracture. Now look at the right. The sample from the hot mold is all rough and torn. That texture tells you the material really fought back and absorbed a lot more energy before it finally broke. That's toughness you can see. And the good news just kept on coming. The hot mold didn't just make the plastic tougher, it also made it stiffer and more resistant to bending. On this chart, you can see both the blue diamonds and red squares are way higher for the 85-degree samples. That means it's much harder to bend it out of shape. And that extra stiffness, that's a huge deal. It's absolutely crucial for any structural component that needs to hold its shape when you put it under stress. You know, exactly what you need for an automotive part. And the hot mold delivered 2 more big wins. It bumped up the plastic's density, which means the polymer chains pack themselves together more tightly. And maybe most importantly, it seriously raised that heat deflection temperature. Those higher red squares mean this new and improved plastic can now survive in much hotter environments without warping, like, say, under the hood of a car. Okay, so let's switch gears and talk about that second variable, the nanofiller. What happens when you mix in these tiny microscopic particles of calcium carbonate? Well, it turns out to be a classic engineering trade-off. So here's the deal. Adding the nanofiller is kind of like adding tiny little bits of rebar into concrete. On the one hand, as you see on the right, you get some big gains. The material gets stronger, stiffer, and it can handle more heat. But nothing's free. The trade-off is that you lose some of the original material's ductility and impact strength. In other words, it becomes a little more brittle. And this slide really drives that trade-off home with data. Look at graph A. This measures elongation at break, which is just a fancy way of saying how much the plastic can stretch before it snaps. The 4 bars on the left are the plain plastic, but look at the 4 on the right with the nanofiller. They're way shorter. They just can't stretch as much anymore. They've traded that flexibility for strength. And yup, the microscope tells the exact same story. Image A is the plain PA6 with that rough, tough-looking fracture surface. Image B is the new nanocomposite. See how much smoother that break is? That's the visual proof of what the data just told us. It's a stronger material, but definitely a more brittle one. But let's not forget about the upside here. The gains in stiffness were really impressive. Just by adding a tiny 3% of this nanofiller, the researchers got up to a 34% increase in the material's flexural modulus. That is a massive performance boost from a really small change to the recipe. All right, on to our final variable. What about the speed? The speed at which you inject the plastic into the mold. Does a faster fill give you a better part? You might think so, but the results here were actually kind of a surprise. Now, if you look really, really close at the microscopic level, you can see what you'd expect. In theory, a faster injection should mix everything up better. And it does. Image C from the slow injection has some bigger clumps of that filler. Now compare that to image D from the fast injection, the particles look much more evenly spread out. But here's the twist. Even though the mixing looked better, it didn't actually matter when it came to performance. The researchers found that for almost all of the important properties, toughness, stiffness, strength, the injection speed had pretty much no effect. It was a wash. So let's put all the pieces together. We've looked at the hot mold, the nanofiller, and the injection speed. So what's the final recipe? What's the best way to make the best possible version of this plastic? This summary table right here is the ultimate recipe card. It lays it all out, plain and simple. First, use a high mold temperature. The arrows show it improves just about everything. That's a no-brainer. Second, add the nanofiller. It gives you a huge boost in stiffness, but you have to accept a small hit to your toughness. And finally, injection speed. The data says keep it low to hang on to every last bit of toughness you can. So the final recipe is clear. A hot mold, add the nanofiller for strength, and use a slow injection speed. What's so cool about this study is that it's a perfect example of how tiny little changes in the manufacturing process, just a tweak in temperature, a pinch of nanoparticles, can completely revolutionize a common material. It unlocks its potential for all new high-stakes applications. And it leaves you wondering, what everyday material is going to get a high-tech makeover next?